Okay, so good morning once again. So we're going to start today's class, and we'll be looking at Ethernet switching. I know some of you missed it the last time, and it was a little bit rusty, but today I think I fixed the slides. It's fine. So let's quickly go through it. It's quite a lengthy topic, but then it's very important because once you don't get it right, it becomes a bit of a challenge understanding other aspects of this whole networking, switching, routing thing. So let's just try and get through it and then we call it a day. Sure. So Ethernet switching. So in this particular lesson, we'll be looking at a couple of things. We'll talk a bit about local area networks. We'll be looking at network topologies. We'll look at the MAC address table. We'll look at MAC address aging. We'll do ARP, that's app. Also, there's so many other things, right? So let's quickly get into it. Before we start, let's do a little bit of a recap. In our prior classes, I think when we're doing the models, yeah, protocols and models, we touched up on the OSI model and we spoke about the physical layer. You know, the physical layer basically defines the characteristics of the medium used to transfer data between devices. So that's talking about the, be it wired or wireless, those kind of things, right? So there we are looking at the voltage levels, we have the maximum transmission distances. So let's say we know for something like Cat5 or Cat6 cables, you can go a maximum of what, 100 meters, right? Good. Now we also know that is where digital bits are converted into what, electrical signals, right? So for wired connections, we know it's basically electrical signals, and then for wireless, it's converted into what, radio signals. But now let's look at the data link layer as well, then we can proceed. Now, we know for the data link layer, it tends to provide node-to-node connectivity and data transfer. For example, let's say me connecting my PC to a switch, me connecting a switch to a router, or me connecting a router to a router. That's kind of a scenario. That's what mainly our switches tend to what, look at. Okay. Now, and in this particular layer, it defines how data is actually formatted for transmission over our physical medium. So, for example, our copper UTP what, cables. Okay, so it's an entire standard that defines how we use these cables or how we terminate it. Now, it also has the ability to actually detect and can correct physical layer errors, right? So that's one of the abilities of our data link layer, if we remember very clearly. And the reason why we say it can detect and correct, some of its features basically make it possible. For instance, if I have issues with EMI interference, right, when I send data and some of the things are changing from zero, the bits are changing from 0 to 1. Now, the Ethernet layer has a way of actually detecting if the packet has been altered or the packet hasn't been altered, right? Then it also uses layer 2 addressing. So depending on the protocol in layer 2 you are using, any type of protocol there has their own addressing standard. So if we are looking at the MAC, you know the layer 2 is divided into two main. You know the layer 2 is actually, okay. So kindly, come on, how do I even do that? Okay, fine. I'll work on it. Right. So kindly, with layer 2, we have two main parts of it. We have the MAC, that's the media access control portion of it, and then we have the logical link controls. Now, so the media access control deals with direct connection between devices inside layer 2. So, like from PC to switch, switch to switch, those kind of interactions. And then they use MAC addresses. When you go to the logical link control, that's the higher level, you realize that there too we have various protocols that work. So you have things like your frame relay, you have your PPP, you have your MPLS, you have all those other protocols there. And they also have their own addressing systems, which they basically use to establish their connection. So it has layer 2 addressing there. Right, good. So we know switches operate inside of our layout, our layer 2. Now let's look at some network topologies. The main topologies we have out there are basically our bus, our ring, and what our star topologies. Okay. Now with the topology, no, please hold on for me. No, sorry about that. Yeah, sure. So, when we say topologies, topologies basically define the physical or logical layout of our computing systems, or let's say of our network. Okay, so either physically, that is how we are physically connected cables, devices together. Now, when we say logical, we are looking at how data actually moves from one device to the other device, right? Now we have so many topologies out there. We have bus, we have ring, we have star. I know you might have heard of other ones like the hybrid, the extended star, the mesh, so many different types of topologies. But then these are the three major ones I would want to talk about. The others are not really in use these days, and even this, most of them are not really in use. So we just would want to restrict ourselves to just these three. Right? So let's look at the first one, which is the bus topology. Now, in a bus topology, usually cables are on a single carrier, like you see here. When it was first initiated, we have a single carrier cable, usually a coaxial type of cable. Can you stay with me? They class. Yeah, woman, no. I like you day class, so if you join, come on. Oh, okay. Okay, sure. Um, okay, sorry. I think I have connection back. Yeah. So, like I was saying, sorry about the call. With the bus topology, we have the case where we have a single carrier and all devices are hooked onto the carrier via cable. So I can see all these devices are there and only one device can actually use the carrier at a time. So where we have this green PC trying to send data, it's the only device that can actually send. And we in the previous class we learned of this CSMA, what CD, career sense multiple access collision detection, right? So we saw how that basically worked, and we saw all of its issues. Okay. Please, who else is having issue with my screen? Can everybody see my screen? Can you see the shared information on the screen? Mary, can you see? Fred, can you also see? Fred, can you see it? Okay, Ransford, is it better now? Oh, okay. I still see the oversight though. Yeah. Okay. Let me see. For your sake, let me just. I know it's from your connection though, but then let me just stop the sharing and share it again. Maybe it might fix it for you at your end. But I'm sure it's from the internet connection at your end. Let me stop the sharing. And then let me share once more. And let's see if it fixes it for you. Has it been corrected? Ransom, has it been fixed now for you? Okay. which I'm sure it's going to be a connection issue from your end. Maybe today your internet is being a little bit slow. That's why you're not getting it instantly. But I'm sure we might work along the line. Okay, sure. So I believe you can see it now. So good. So this is for the bus topology, right? So we know it's usually a linear bus, and everybody is connected to that particular bus, and the only one device can use it at a particular time. When more than one device tries to use it, we know what happens. You know, there's definitely going to be a collision, which is going to create problems, right? Now, so apart from this, now here are some of the hardware which we used for our bus topologies back in the day. So here you see this is a BNC connector that basically you have your, that's the cable I was talking about. So this is like a serial, your single carrier. You just keep on hooking up. This is a point where you connect the PCs from. So the PCs equally have a cable and you just hook them up into this particular portion. These are other hardware as well that were required for that kind of connection to take place. Though it is not um, though it is not really too much like that, right? Okay, good. So that's good. So with the ring topology happens to be the a different. That's the it was introduced by IBM. So usually people say the IBM token ring topology, where it was just like a bus, but then this time around it was in the form of a ring, where a PC would require a token before it would be able to send anything on the network. So if you don't have the token, you can't actually what send data off the network, and it goes in the form of what a ring. If one PC should break off in the ring, the entire ring goes off, just like the way you have it for your bus topologies. If a single device goes off or someone kicks it, then you're in trouble. Like the entire network is down. The same thing applies to your ring topology. So most often you'd have data move in the form of a ring like that, right? Now this is a typical hardware that was used in the IBM token ring. So it still had Ethernet ports, just that the way the whole thing is connected, it forms some form of what? A logical ring in the way data actually moves. So it's not like you see us connect one device to the other to the next like that. No, you would use something like this, but then the way data is actually sent from one device to the other is in the form of what? A ring. Now let's look at the star topology. Now with the star topology, we would usually have a single device in the middle that every device is actually what hooked up to. So it would be a multi-port device that everybody is hooked up to, and data has to go to that device before it goes anywhere else, right? And a typical example of the first star topologies we implemented was with the hub. Though hubs physically the connection looks like a star, but logically how data is transferred is actually a bus because we know a hub is still one collision domain device, right? So that's basically how our hubs look like, or this is how the first star topologies that were implemented actually look like. Now, with our modern style, however, we tend to implement switches because you know in this kind of topology, we still are likely going to have what a collision going going to occur, right? So you see, we can have collisions in the hub environment, but I think we know this already, right? So we know a collision is a group of network devices that will simultaneously what detect a voltage spike, and we know that's how collisions happen. If more than one device tries to send at the same time, you know, you tend to have what 10 volts on the line, and that is what creates the collision, and then they all have to reset and send and try to send again. But in our modern networks, we are now using what switches, right? And that's our focus for this particular class where we see how switches basically work. So now when we talk about layer two, we don't really look at how hubs don't even reside inside layer two. Hubs are found inside layer one. But inside layer two, the primary device we find there is basically what? A switch. Right. Now, so in this particular lecture, we'll focus on how switches tend to work. So let's proceed. Now, the first thing I would want to talk about is a local area network. We all know what a LAN is, right? Now, if you look at this topology we have on our screen, the device that defines a LAN for us is basically a switch. So here I have so many different types of networks. So if you look at the first example here, the green network, I have a router which hooks up to the internet. In there, I have a single switch and I have 3 PCs attached. This defines one local area network. This is one broadcast domain. And I have 3 collision domains in there because I have 4. 1, 2, 3, 4. I have 4 collision domains in there, but then it is one broadcast domain, which is one network. It is one LAN. When you come to the second topology, that's the red one, you'll find out that I have 2 switches. Now, this doesn't mean I have. Yes, that's how hubs basically works. So hubs, so Ransford was asking a question, was like, does it mean that hubs will broadcast information to every host on the network? Yeah, sure, that's how hubs, they basically work. Every information that you send is relayed to every other device connected in there. Right, okay, sure. So now when we come here on the other hand, on this topology. So with the red topology, I have 2 switches, but it doesn't mean I have 2 networks. When you stack up switches together, all you are doing is you are extending the network, but it's not like you are breaking them out. So this is still one big local area network, because it does happen. Sometimes I'll buy a switch and it's an 8-port switch, but then along the line, I realize that I need to expand my network because the ports are getting full. And the only option I have is basically to buy another switch and add it onto that particular switch to expand it. So this is one single network. However, when we come down here to the blue, realize I have one router here, but then I have an interface coming out of the router here. So this is one network on its own. So I have one network here. Then when you look on this side, you have another network coming out of the router. So on this particular downside here, we have 2 different local area networks. It's not one. Because here, although we have 2 switches implemented, there's a router breaking them up. Yeah, there's a router breaking them up. So this is what we saw. So I always tell people, it's basically your switches that define a local area network. Once I have a switch, I can say I have what? A local area network in place. Okay, so let's proceed. Good. So assuming we wanted to send information from this PC here all the way to this other PC, which is what this particular class is about. So we'll get to see what all of that basically was. Good. So let's look at the OSI model again in terms of data PBDs. Now we know as data is in layer 7, 6, and 5, we still call it what? Data. When we move down to layer 4, we add an extra information out there, which is the layer 4 header, and then data changes to become what? A segment. Right. When we move to layer 3, an additional information is added, which is the L3 header, then data becomes what? A packet. Then when we move down to layer 2, we have 2 extra information added. You can see we have a layer 2 trailer, and we have a layer 2 what? Header, and we tend to call it what? A frame. But then all together, this is referred to as what? PBDUs. That's protocol data units. Please don't forget it. You might hear them say PBDUs. So someone might say, oh, I have a layer 3 PBDU. I have a layer 4 PBDU. You should know what it basically means. It's just saying the segment. So if I ask you, oh, what's a layer 4 PBDU called? You should know it's a segment. You should know it's what? Maybe layer 3 is called packet. Layer 2 is called what? A frame. It's very, very important to understand these words and know which layers we are talking about, because it's a common question that pops up usually in the exam, because then the phrase, there's a sentence and they might mention segment, they might mention packet, they might mention frame. Once they mention these things, you should know, okay, so if it's a segment, they're referring to something in layer 4. If you're talking about packets, I'm dealing with routers. They're talking about something like that. If I'm talking about frames, then I'm dealing with switches. So please know where each one of these things were basically for. For this particular class, our concentration is much more on this layer 2 frame. All right, so let's look at it. So this is how the frame looks like. I'll have a header here, and I have a trailer at the other side. Then I have the actual payload, which is my packet encapsulated into it. I believe we all still remember encapsulation very well. So they have 3 packets encapsulated in the, which we can equally call a payload. Now let's take a look at the content of your Ethernet header, right? In the Ethernet header, we have a couple of things. We have a preamble, we have an SFD, which means start frame delimiter. We have the destination, which contains our MAC addresses, that's our destination MAC address. We have the source, which will contain information about the source MAC address. And then we have the type, which defines what type of, what type of data we are actually trying to send. Or sometimes it can be used to depict the length of the packet that's actually being sent, or the length of the payload, let me put it that way. Then at the end of it, we have a trailer, which contains something else, which is the FCS, that's the frame check sequence. Okay, so we'll look at each one of them into much more closer details to understand what they do. So let's look at the preamble and the SFD. So your preamble happens to be 7 bytes in length. That's basically 56 bits. And it's made up of an alternating ones and zeros. You have it looking like this. So I have 101010 times 7. Then what it does, it's used to make sure devices can synchronize their receive clocks. Like what this means is, it's more or less like telling the device, hey, you're about to receive data, so get yourself ready. That's what basically the preamble does for you. Now with the SFD, the start frame delimiter, it has a length of 1 byte, and it's equally an alternating ones and zeros, but then it ends with what? A 1. So it looks much more like this particular one. So your SFD is at the end of your preamble, but it is a preamble that is used to allow devices to synchronize their receiver clocks. So kindly do not forget this. Okay, now let's look at the source and the destinations. So basically, they allow you to show which device you are sending or receiving a frame from, that kind of a thing. So it's more like the addressing aspect of a frame. So it puts in the sending or receiving device addresses. So it consists of what? MAC addresses in there. So you have destination or source MAC addresses. That MAC is what? Media access control. Please don't forget it. And your MAC address is made up of 6 bytes. That's 48 bits of information. So it's a 48-bit address, and it's a physical address, which means it is embossed directly on the hardware itself. We'll talk of MAC addresses soon. So let's leave it. Just know that it's 6 bytes in length. That is, it's a 48-bit address, and it's a physical address which is embossed directly on your interface card. Okay. Then with a type or length field, it's made up of 2 bytes. That's 16 bits worth of length. That's how much, that's the size of that particular field. And the value in there, if it happens to be 1,500 or less, it basically indicates the length of the encapsulated packet. That's in terms of bytes. That means the payload you have in there, what's the size of the payload? That's what this would do. However, when it is 1,536 or more, that is used to indicate the type of packet being encapsulated. Okay, so it will let you know whether it's an IPv4 or it is an IP version 6. That's the duty of this particular type or length field. If you check the field and you see this hexadecimal value, that's this 0x0800, that should let you know that this is IPv4. This is hexadecimal. When we do IP addressing, we'll talk about them more, which is equivalent to 2048 in decimal. On the other hand, when you are seeing it look like this, like you see me draw here, that lets you know this is IPv6. As if it's 0x86DD, you should know this is what a IPv6 encapsulated packet. And that would be equivalent to 34,525 in terms of decimal. Okay. So let's go on. The last one, which happens to be the FCS, that's a frame check sequence. Okay. Now this field is made up of 4 bytes of information. That's 34 bits in length, and it's used to detect the corrupted data by running a CRC algorithm. I said the last time, if back in the days when we used to do a lot of copying from CDs. If the CD scratches a little when you try to copy, Windows gives you an error. It tells you cyclic redundancy check error, something, then it doesn't copy again. Because then it does that, it runs the algorithm on the CD and it knows how much data is actually supposed to be there. But then when it runs it again, it's no longer the same data, so it won't copy actually, right? So that is what allows your layer 2, that's your Ethernet frame, to be able to detect errors in a connection. Like I was telling you earlier on, is this particular FCS that gives it that kind of a capability to be able to do that. All right. So let's look at the total size of our Ethernet frame. So we know the preamble is how many bytes? It's 7. Your SFD is 1. Your destination makes up 6. Your source also makes up what? 6 bytes. And then your type is made up of what? 2 bytes. And your SFC is made up of what? 4 bytes. In all, which means the Ethernet frame without the payload is what? 26 bytes. That is header plus trailer. It gives you a total of what? 26 bytes. Right. So now let's look at MAC address. Please don't forget, these informations are kind of very important. These things you see here, this byte sizes and stuff. Sometimes they might just throw it in there, and once you don't get it, it becomes a little bit of a hassle. So don't forget them. Just know that your Ethernet frame header without the payload, which is the packet, is a total of what? 26 bytes. Okay, though we might see that sometimes it's not always like that. So now let's take a look at the MAC address. So our MAC address, we already know is 6 bytes in length, which is 48 bits long. And it is physically embossed on the device when it is made from the manufacturer. So we call it a bend-in address. It is there, it's physical, it's permanent, you don't change it. It is globally unique for every device. That is how it's supposed to be. Unless you go and buy cheap devices, then you're likely going to come across 2 devices having the same MAC address, but it rarely occurs though. Then you have your first 3 bytes representing the manufacturer. We call it the OUI, so that's the organizationally unique identifier. So if I have Cisco equipment, we'll notice that all of them would come with that same first 3 bytes of information is the same, whereas the last 3 bytes are unique to the device itself. So that's more like the device's serial number, right? I think we have devices here, so we would check it. Or even when you do packet tracer, you would have a similar experience. So I would use the devices to check for you to see what we are talking about. But however, when we're writing our MAC addresses, we write them as hexadecimal. So it's written as 12 hexadecimal characters. And you have an example here. Every vendor has a way they write their MAC address. So Windows would write MAC addresses, separating them with what? Hyphens, like you see here. If you're in a Linux environment, you're likely going to see them write it and separate them with what? With colors, right? Like you see here. If you are in Cisco environment, this is how Cisco write MAC addresses. So on most of your Cisco devices, when you check the MAC address, it's written in this particular format. Why is writing the format you write it important? It is important when you are doing a configuration that requires you to actually configure a MAC address. Let's say enter a MAC address. If you don't enter it properly, then it won't be seen. Okay, so let's proceed. So we're talking about how devices are able to learn their MAC addresses, right? And if you look at the small topology we have here, there's a switch. We have a PC on the other hand that has this MAC address of ABCEF00001. Then this guy has ABCEF00003, and that's ABCEF00002. So that for the remaining course of this demonstration, I'll just use the last portion of the MAC address, right? Okay. So let's say this PC, which is PC1, decides to send a frame to PC2, which is down here, right? So you can see the destination is PC2, which is 002, and the source is PC1. That's what you see here, and that's what you probably see here, right? Now, when they try to do this, at this point in time, a frame like this is known as a unicast frame. It is a frame which is destined for a single target. So in this case, we have PC2. So this is called a unicast frame. It is a frame destined for a single target. Now, what happens? PC1 would have to forward the frame to the switch. So it forwards the frame to the switch like this. Now, when it forwards it to the switch, a few things will need to happen. Okay, so Ransford, welcome. So we're just basically trying to, let me just go back a little bit, then we proceed. Guys, please pardon us. But, so I'm saying there's a little topology which is trying to explain to you how switches are able to learn MAC addresses, right? Because unlike hubs that basically forward everything they receive out on every other port, switches are not designed like that. Switches are devices that break up collision domains. So for a switch to be able to do that, it has to learn the location of a device so it can forward the traffic or can forward the frame directly from destination to source. It doesn't have to send it out on every active interface on the switch, right? So let's see how that goes. So I'm saying we have PC1 here, which wants to send the frame to PC2. So it generates the frame, you see it there, which has the destination of 002 and a source of 001, like you see. Now, this frame is referred to as a unicast frame, okay, because it's destined for a single target. What PC1 then does is it forwards the frame to the switch. Now, when the switch receives this frame, it looks at the frame because it has to educate itself. So it knows where the devices are and how to send their responses to them. It does that by having to populate its MAC address table. So switches keep something known as a MAC address table or a CAM table, C-A-M, CAM, like this. So they either keep a CAM table or a MAC address table. And it's basically a table that contains all the MAC addresses they have learned and the ports on which they learned those particular MAC addresses. So when it receives this, and it is only the source MAC addresses that end up in this table. So if it looks at this, it says, oh, okay, so you are PC1, here's your source, right? Good. So I have just learned of you, let me put you inside my MAC address table. And it does just that. So it puts PC1's MAC address in there. But then when it looks at the other one, it doesn't know them and it has to learn where they are. Everything you put into your MAC address is called, or when a switch is able to learn of a MAC address, we refer to it as a dynamically learned MAC address, or we call it dynamic MAC addresses. That is how they are basically called. So the switch is going to do something else because it has to figure out who this particular MAC address belongs to. So it does that by again having to forward the frames out to get to learn it. But this kind of frame is called an unknown unicast frame because it doesn't know where it's going. It has received it, yes, but it doesn't know whose MAC address this is. And it has a responsibility to now go ahead and what? And learn. So what happens to unicast frames? All unicast frames are flooded out of every existing port. So for the switch to be able to learn this, it has to flood it out to every other device out there. So except where it came from. So it will flood it out like this. So you see that now we would have a frame come down here to PC2, another frame go to PC3. But this is what happens. PC3 would ignore this particular frame. The reason being that when it checks the destination MAC address, it doesn't match his. This is 2. PC3 has a MAC address that ends with 3, so it just ignores it. But however, PC2 would accept it. If it's something that it has to process, it processes it. If it doesn't have to send a reply, it ends there and it doesn't send anything back to the switch. It just takes it and then that's it. But let's look at a different scenario. Now, in this scenario, let's say PC1 does the sending again. The same thing is going to happen. It forwards to the switch. At this point, it's an unknown unicast frame because the switch doesn't know of where PC2 is and where PC3 is. It doesn't know who owns this MAC address. It learns of PC1 first. Then after learning, it goes ahead to what? Forward the frame out to everybody. PC3 rejects it again. But then this time, if it's something that PC2 needs to send a reply back to PC1, this is what is going to happen. PC2 then grabs a new packet. Do you realize that now it has changed? Now you have destination being 001, which is PC1, and the source is now what? 002, which is PC2. So it then now what? Sends that frame to the switch. When the switch receives it, it realizes that, hey, I've learned of a new device, because when you look at the source, it's a new source MAC address. So it will do what? It puts that info inside its MAC address table, like you see here. Then, this time around, it won't flood this frame out. The reason is simple, because this frame is a known unicast frame. The switch already knows PC1's MAC address. You see here, it has already put that MAC address inside its what? MAC address table. So there's no need to flood it, but rather, for known unicast frames, they are forwarded to the destination device. So it will just forward it straight to PC1 because it knows where PC1 is. It knows PC1 is connected on its FA0/1 interface. We're good. So this is how switches tend to what? Learn MAC address. Okay. Now, when a switch learns a MAC address, please be careful. MAC addresses don't stay in the MAC address table forever. If not, there's going to be a problem, because if you find yourself in a very huge network, so many machines, what happens? The MAC address table will be overpopulated. But then in switches, all dynamically learned addresses are removed from the MAC address table after 5 minutes of inactivity. So if the switch learns of a device and for 5 minutes the device hasn't communicated on the network, it just removes it from its MAC address table. So the table doesn't end up being filled with junk addresses which are not really active on your network. So know that after 5 minutes, the switch flushes any inactive device from its what? MAC address table. Right. Now let's look at a different network scenario here. Here we have 2 switches and we have 4 devices attached to them. So we do a different scenario. This time around, PC1 wants to send data to PC4. Let's see how in the 2-switch scenario this is going to work. Don't forget, this is still one what? Single network. This is one big network, right? So let's see what this happens. PC1 generates the frame again, right? We assume it already knows the frame, so it knows where it's going. It wants to go to 004. The same thing happens. At this point, it's a unicast frame. It forwards the unicast frame to the switch. At this point, switch 1 doesn't know the destination, that's 004. So this is what? This is an unknown unicast frame. And we know what happens to unknown unicast frame. It will be what? Forwarded out of, or let's say it will be flooded out of every port except where it came from. So switch 1 then floods this particular frame. What does it do? It sends it to PC2 here. and then it would send it to switch 2. PC2 would reject this frame or would ignore it because that's not its MAC address. But when it gets to PC switch 2 here, what happens? Switch 2 also says that, okay, fine, I'm just learning of somebody new, so let me put it in my MAC address table. But do you notice what is happening here? Switch 1 learns of PC1 through this interface. Switch 2 is learning of PC1 through its F0/3 interface. So that is what is going to put in the MAC address table. Then switch 2 goes ahead to what? Flood the frame again because it doesn't know where PC4 is. So it does that. It will flood the frame like you see here. So it sends it to PC4, it sends to PC3. PC3 would what? Ignore it because it's not its MAC address, but then PC4 what? Would accept it. Now, if PC4 has to send a reply back, it will create a new frame. Here it's going to what? Swap out. So now the destination is going to be 001, which is PC1's MAC address, and the source is going to be 004. This is a unicast what? Frame. It sends it out. Here, switch 2 knows where this MAC address is. So this is also what? A known unicast frame. It won't flood it out of every interface, but rather it will forward it to where it knows it can reach that particular device. So it first will store the source MAC address in the MAC address table. That is for PC4. You see 004 being put in the MAC address. Then it forwards it out to PC1, to switch 1. Switch 1 receives it. It looks at the frame and realizes, okay, I'm learning of a new device. It has a MAC address of 004. So switch 1 will also what? Populate its MAC address table. Then it realizes, okay, it's destined for 001. This is a known unicast frame. I know how to get to this device because it is in my MAC address what? Table. Then it forwards it directly to what? To PC1. So this is how switches learn MAC addresses, and this is how they forward your frames what? Around. Before any switch can forward any frame, it should first of all know where the MAC address can actually be what? Be found. Okay. So a quick one, let's look at our Ethernet frame again before we continue with the rest of the demonstration. Now, sometimes an Ethernet frame doesn't always.
Hello.
Yes.
My hand is up.
Okay, sure. Sorry, I didn't see that. Sorry.
Yes, I want to know. You see, can a switch learn more than one MAC address via the same interface?
Yes.
Okay.
Yeah, a switch can learn more than
Because
one MAC address via the same interface. Let's assuming PC2 also decided to send a frame to, let's say, PC3. That frame will leave PC2 here. It hits the switch. The switch will store PC2's MAC address in there. So we'll have a new entry, which will be 2 here. On the port it's learning it from, the port becomes F0/2. Then it forwards it out to switch what? Switch 2. When switch 2 receives it, switch 2 will put the entry there because it has length of this MAC address. So now when you come to switch 2, you have another entry. You have your 002 like this, and it will be learning it out of F0/3. You get it?
okay.
So a switch port can learn more than one MAC address via a single interface.
Okay.
Is it clear?
Yes.
Okay, sure. That's clear. Okay, so let's proceed. So like I was saying, sometimes your Ethernet frame will not come with this preamble and SFD. It's not always it comes with it. Sometimes it's just going to be made up of what? Of the destination, the source, and the type. We don't usually consider it too much as part of the Ethernet frame. Okay. And the minimum size of your Ethernet frame you can get. Okay, well, let's say the minimum size of an Ethernet frame, that's header plus the payload, is 64 bytes. Okay, the minimum size is 64 bytes. Okay, now this 64 bytes, we already know that if this destination is 6, source is 6, this is what? 2, and that is 4. Which means your payload can be a minimum size of what? 46. Because when you subtract, this is 12, that's what? 14, and then subtract 18. So it means your header plus your trailer most of the time is 18 bytes. When you subtract it, it means the minimum payload, this payload you see here, or this packet, the minimum it can be is what? It's basically 46. Okay. Now, however, if your payload happens to be less than 46, maybe you deliberately send a payload of 36 or maybe 30 bytes, it would have to be padded with additional zeros for it to become what? 46. You need to add 0 padding to it because that's a minimum payload size which is allowed. We'll do a demo of it to see what I'm talking about. Right, so let's go on. Right, good. So that's enough for our Ethernet frame. Now let's look at the real thing, how devices actually learn MAC addresses. In the first scenario I gave you, I was just giving you a scenario where your PC had already been able to learn the MAC address to make the understanding easier. But in a real life network, what actually happens is this. Before any PC can send out anything out there, it is the PC's responsibility to learn the MAC address first, because it is the PC that informs the switch where it wants to go to, like which device it is looking for, and not the other way around. And this learning of MAC address is done using a protocol known as what? AP. So that's address resolution protocol. It is a protocol used to resolve what? MAC addresses to IP addresses. Okay, so we are going to look at a scenario for us to understand this very well. But let me just go over it again one more time. What I'm saying is, for a PC, before a PC goes out to reach another device on a network, the PC first has a responsibility to know the MAC address of that device. And it does that by relying on the what? Address resolution protocol. Okay, so if you see a standard frame, it will look like this. You have source IP, you have destination IP, you have the source MAC address, but the destination MAC address will be what? Will be blank. This PC is not going to know it. It would have to figure that out before it can send the actual frame to the device. So let's see how that goes. We have PC1 who's going to try to send something out again, and let's see how it's going to work. So first of all, we are going to have this information in there. We're going to have what? An IP address added to this network. And PC1 has .1, PC2 has 2, PC3 has 3, PC4 has 4. So that's 192.168, 1.1, 1.2, 1.3, 1.4, like that, right? And that is what gives us an ARP request like this. So before PC1 can go anywhere, it first of all has to what? Generate an ARP request, like you see here, right? So it would rely on this and generate the request. So let's look at ARP. I think I should have printed that slide. Sorry. So this ARP stands for Address Resolution Protocol, and it is used to resolve layer 2 addresses of known layer 3 addresses, that's IP addresses. So you know the IP address, you don't know the MAC address. So ARP is responsible for figuring that out for you. Then you have, it consists of two main messages. You have an ARP request, and then you have an ARP reply. These are the two main messages that make up your address resolution protocol. Your ARP request is a broadcast frame, which means it's a frame that goes to every other device on the network. Whereas your ARP reply is a unicast frame. It is a frame sent to only one host in the network. That is basically the requesting host. So if PC1 wants to learn about PC4 and it sends an ARP request, which will be a broadcast, when the reply is coming back, it's going to be an ARP unicast frame, which is the reply, and it's going to be sent to only PC1. Okay, so let's look at our diagram again. Right? So we have our network, which is looking like this. We have our 192.168. Now we are going to see how the LAN stuff up. So PC1 crafts an ARP request, and this is how an ARP request looks like. It's 192. You have your source IP, you have your destination IP, you have a source MAC address, which will be PC1's MAC address. You see it here. But then the destination MAC will be all filled with what? Fs, which is the broadcast MAC address. So in an ARP request, anytime you see this FFF, which means this particular frame is intended for everybody on the network, right? It's not only used in ARP, but there are several other things that happen in your network that would rely on this FFF, right? So if you're analyzing traffic and you are looking at the destinations and you see this, no, it's something that everybody received, okay? So know it. So that's the broadcast MAC address. Okay, so let's proceed. So you would have PC1 generate an ARP request, like you see there, and it follows a similar process like we did. It sends this ARP request out. Now, when it hits the switch, don't forget the ARP request is going to contain PC1's MAC address. So the switch has a responsibility. It will learn the MAC address instantly. So it learns it and populates it in this MAC address table, saying, "No, I've just learned of you." Fine. At this page, we still call it, this is a unicast what? Frame. So it sends it out because if it looks at the rest of the information, it realizes, okay, this is something I'm supposed to send to everybody apart from where it came, because it has all Fs. The switch knows it's a broadcast what? Frame. So it sends it out to everybody. So it will go to PC2. PC2 will look at it. It will reject it because when it checks the IP address, it realizes I don't have an IP address of the 4. When switch 2 receives it, it also learns of PC1 and puts it in its MAC address. So it populates it out there. It also has a responsibility to what? Flag it out. So it flags it to what? Both PC3 and PC4. PC3 is also going to what? Reject it because when it looks at the IP address, it is 4 and PC3's IP address is 3, so it rejects it. But when PC4 looks at it, it realizes, hey, this is my IP address. So it would have to what? Respond to it. So it responds by generating an ARP reply. Sorry for this, I would have to correct it. Let me just correct it quickly. Hold on, let me just correct it. I don't want to. Okay. Okay, sorry. So I fixed it. Yeah, sure. So you have now PC4 is actually going to generate what? An ARP what? Reply packet. So you have it generates a reply, and the reply would look like this. Realize now the source is going to have an IP of .4, which means it's coming from PC4. The destination is going to have .1 because it's intended for PC1 as we see it on the other side. Then it forwards it to the switch. I have a hell of a job to do, but don't worry. Let's go on. I'll correct it after the class. Just know this is not a request. This is supposed to be a reply. So let me just fix that. So let me just write E here. So this is supposed to be a reply. So it generates the reply. And this time around, always know that since switch 2 already knows where this MAC address is, right, which is PC1's MAC address, this FDD is. So it's what? A known unicast what? Frame. So it doesn't flood it out, but rather the forward sits to what? To this particular PC. That's to this particular switch, that's switch W1. And then switch 1 in turn also knows where the PC is. But then what happens? It has found new information. There's a new source MAC. So it will populate its MAC address table first with PC4's MAC address and where it's learning it from before it goes ahead to forward the ARP reply to PC1. Once it does that, now PC1 knows of what? Of PC4's MAC address before it can actually send the real data it wants to send, right? All computers keep an ARP what? Table, just like the way switches keep MAC address tables. All computers also keep what? An ARP table, and the ARP table contains all the MAC addresses they have learned. You see, we have static entries, and then we have dynamic what? Entries. So if you want to check your ARP table, the command is ARP hyphen what? A, that is be it for Windows, be it for Mac, be it for Linux. All of them what? Do things like that. So always know it has portions. If you look at it, we have internet address, which would basically be your IP address as a layer 3 address. Then it has a physical address, which would be the MAC address of the device. And the type specifies how it was learned. So if you see static, it means it's a default entry. And then if you see dynamic, it means it was learned via what? ARP, right? So like the example we have here, if you look at it carefully, we have what? A dynamic entry, which has just been what? Learned, right? Okay, sure. So the next thing we will have to do is a demo, right? For us to see how ARP basically works. Okay, and here I'm going to be using GNS3. Okay, so give me a sec while I pull that GNS3 topology up. Now, we all know GNS3 is also what? It's another software we use for our practice. However, this is an emulator. So it uses the real Cisco IOS, and almost all commands that won't work in Cisco Packet Tracer actually tend to work inside GNS3. Right, so it will work here. So let me quickly start it up. Later on, we should have a video on how to set your GNS3 up. I'll post a link on the video for you. Those who want to install it, though it is resource intensive. So if your machine doesn't really have too much of resources, please don't try using GNS3 because then it's going to freeze you up a bit. Okay, so I have a similar topology already built, and we are going to use it to see it. The reason why I'm using GNS3, it has a feature which allows you to actually sniff on packets or capture packets, relying on a third-party tool, which is called, how do you call this? Wireshark. Yeah, so this is my GNS3 topology. You can see that. I believe you can all see this topology, right? So I have a couple of PCs. So I have PC1, PC2, PC3, PC4. And these PCs have been configured with IP addresses. So let me just turn them on first. So I turn on all the PCs. They are on. And let me check if the IPs haven't changed. So I just have to right click and then open the console. But I would want you all to at least install the GNS3 as well, so you can get to have a feel of it. All right, so let me quickly check the IP address and user commercial IP. Now, the reason why I'm using show IP is because it's a Cisco product, and almost all Cisco devices would use show IP. Unfortunately, I don't have any type of IP addresses on this thing. I think it has been cleared for a strange reason. So I'm just going to set one up quickly. All right, so it's IP, and then I just put the IP I want to use. So this is PC1. That's 192.168.1.1. Then I follow up with a subnet mask. which is 255.255.255.0. So it will check if there are any duplicate addresses. There aren't any. So I've set for PC1. Now if I do the show IP, you can see it now has an IP address. That's the only challenge with GNS2E sometimes. When you use the virtual PCs, it doesn't save it. I don't know why it does that. Yeah, it doesn't save it. So let me go ahead and open the other ones and quickly put IPs on them. So let's do console for you as well. Console for you. Okay. Why are you opening 20? Okay, so let's go to PC2 and do the same thing here. So just I put my IP 192. I hope you are following 192.168. Sorry, it's 1.2. Then it's 255.255.0. Check for duplicate addresses. Yeah, fine, nobody has it. We do the same for this PC2. It's just IP 168.1.3 255 255.0. Hit enter. Yeah, that has been done. Then this one as well. So we do our IP. Then we do our 192.168.1.4. I have 255.255.255.0. So we are done setting up IPs for all the PCs in this particular topology of ours, right? Now, before we proceed, I'm going to be using a feature of networking, a particular tool for us to see how this works. Let's say PC1 wants to ping PC4, right? Now, what is ping? So ping basically is a network utility used to test reachability of a host. So as a network engineer, it's one of the utilities you'll be using a lot. So you want to check maybe a machine is still alive on your network or it is not alive on your network. The only way you can do that is by pinging the machine. And not only is it used to check the reachability, but then it's used to measure the round trip. Round trip means how long does it take for a frame to leave my PC, let's say PC1 to PC2, and then back to PC1, like the round trip is used to measure that. Your ping also consists of two main types of messages. You have the ICMP echo request, and then you have the ICMP echo reply. To use ping, we type ping followed by the IP address, like the example you see there. So ping, then the IP address you want to follow. So we are going to do exactly that for this topology of ours. Okay. So I want us to, we are going to ping from PC1 to PC4. But there's an interesting feature of GNS3 I want us to use. And the feature is known as the As the capture. It relies on Wireshark, like I said earlier on. So I'm going to start a capture so we can actually analyze the traffic and see what basically happens when we send our ping. So let me start a capture. It's going to start, so I'm capturing from where? My Ethernet 1 to the switch, right? So let me capture it. So let me do OK. Right, you see now I have a zoom, how do you call it, like a magnifying glass on the cable, right? So we can go ahead and now hit our ping. Okay, so you can see where Wireshark is also so we can see Wireshark here. Wireshark is going to start the capture. It tells you it is there. It's actually ready to capture, but nothing has come up. So let me just quickly start this. Let me put this on the side, and then we would analyze it. Let me just put this here. Right. So let me just do a ping. Let me go to PC1, and then we do a ping to PC2, so to PC4. So ping, and then I type 192.168.1.4. Now, when I hit enter, it starts to give me a reply. You can see data is being generated over here. By default, all Cisco devices would send 5 things. Okay, so they send 5 ICMP pull requests, they get 5 replies back. So you can see here, then you have the TTL value, and then you have the time. You see the time here. There's 1 point something something, telling us how long it takes for the frames to get back to us. Now, the ping is done. Let us look at our Wireshark and see if we can actually analyze the whole thing. Right. So let me just stop the capture. Now, let's look at how the whole thing started. Now, do you realize that when I go to the very first frame that was generated here was an ARP? Do you see it? So you have the time 000 private. This is PC1's MAC address. We'll check it, you'll see it. And it tells you destination is what? Is a broadcast, right? Destination is a broadcast, and the protocol type is ARP. It gives you the length of data that was sent was just what? 64. And the info, it tells you who has 192.168.1.4. You are requested to tell 192.168.1.1. Now see the reply you got. This is the second packet. The second packet is here, and you can see it's also ARP. It's a different MAC address. This is going to PC1. If you look at the address, it's the same. But in this case, you see the source is coming from where? PC4. Then we have this. It tells you 192.168.1.4 is at this particular MAC address before the actual ICMP starts. So let's examine the frames itself. So we come here, and then let me expand it. So I expand it. It tells me, it gives me a little bit of information about the frame. It tells me the app. No, I'm not interested in this. Let me look at the Ethernet one itself. Let me look at this. Yeah, this is what I'm interested in. So the Ethernet content. So you see here. So if you look at the Ethernet frame itself, it tells you source, that's the MAC address. Then the destination is FFF. So you see here, destination is FFF, like we said. This was intended for everybody. And the source, this is where it's coming from. Then if you look at the type, so let's wait whilst the others, but you can always catch up. So let's go on. So I think you see the ARP, address resolution protocol request, and that's the content. You get it. So Wireshark is quite a fantastic tool that allows you to analyze and understand your network, so you know what is actually going on in there, right? Okay. So let's look at the reply. So when you look at the reply, it's a similar thing. You see this time around, the destination is intended for PC1. The source is PC2's MAC address. It tells you it's still ARP. The pattern is all zeros. And then the FCS, you see it's generated there, but it's unverified. Nothing really happens. So if you see the reply content too, it has it there. So it tells you sender's MAC address, sender's IP, target MAC address, target IP address, and we have it in there, right? So this is how Wireshark basically allows you to analyze traffic. So let's look at one of the ICMP. So now when we look at the ICMP now, the actual data that was being sent, you see it there. It tells us it's a ping request. So let's look at the request. Right, so you realize the request went after it had length of the MAC address. So if you look at the request one, let's see what's there. It tells you frame 3. So it gives you the bytes on the wire, how much has actually been sent, and the ID and stuff. But then let's look at the Ethernet frame itself. That's what I'm interested in. So we have the destination there. It gives you this. So you get it. Good. So you see the destination It gives you the MAC addresses, private. It gives you, there's a globally unique factory default, stuff like that. Then the source, it tells you the packet type. You see it's 080 800. So that lets me know there's an IPv4 packet which is being sent out there. Now, if you look at the IP header, you also have different sets of information in there. You can see the IP header there. It gives you everything you need to know, differential field and stuff. And the protocol type is what ICMP. We can see it going out there. So this lets you know it's a very good tool to analyze your network traffic. It gives you a better understanding. Then there's the actual ICMP protocol that handles it. So type, it's an echo ping request. It gives you the checksum, identifier, all these things are there. Right, so that's it for this particular demonstration for you to understand how it works. You get it. So always know before any PC can send anything to anybody on any network, it first of all has to rely on what? ARP to learn the MAC address of the device before it can actually send the frame. Right, are we good? Does anybody has any question to ask? But the understanding is clear. We good? Okay, sure. So I don't want to save this, so I'll just quit without saving the capture. Then I can shut down all these devices and then I can close this. Okay, fine. So that's GNS3. I'm done with it. Yes. Okay, fine. So okay. So let's go on. Good. So for our MAC address tables, right? Unfortunately, I don't have any device hooked up. Okay. Let me quickly demo that. At least you have a switch here. The switch on here. The switch is on. The switch is on. So let me quickly connect to it. Okay. So can you give me a sec? Let me grab an Ethernet cable to connect this switch to my PC. Okay. Sure. So okay. So I hook this up to any available ports on the switch like this. I mean, my table is a little bit messy, but you know what? So many wires here. Okay, so I'm going to pull up how do you call it? Putty again, like yesterday we used it. So let me quickly pull Putty up, and I think this one is the serial connection. Let me just put it here so you see what I'm doing. So the serial connection, and that one is on port so 14. Yep. Yeah. So I'm in the switch. I believe you can all see the screen. Okay, so I choose no. No, like this. Right, so I'm going to switch. Now, the command to check your or to show your switch, your MAC address table is basically from privilege mode. All you can do is, so I first have to do enable like this. Then I do show MAC. Now, this is a recent device, so I can just do show MAC. If I do a question mark, it tells me what I can put in there, right? So show, and I can leave a space and just put show MAC address what? Hyphen table. So show MAC address hyphen table. Now it will give me so many things there. You can see the MAC addresses there. Now most of them are static, and it tells you these are the switches MAC address itself. But then there's one entry there. Do you see the entry? This particular entry. This is my PC's entry. The device I just connected to the switch. The switch has lent its MAC address on that particular port. Again, so this is how your switch's MAC address table would look like. Okay, but then you have static entries, and you can see that is what is a dynamic entry. That's a dynamic entry we have out there. So that's our MAC address table, and that's how it looks like. If you want to manually clear a MAC address table, you use the command clear MAC address hyphen table dynamic. That will clear all entries. But if you want to clear a particular one, then you might have to just do it once. Let's try it and see if it will clear. So clear MAC address. So you see a clear MAC address table. Sorry, I have to specify it's dynamic. So dynamic, and it's cleared. Let's see if I'll still have it. But I know it's likely going to show there again. Yeah, it's cleared. You can see I don't have my MAC address in there anymore because I manually choose to clear it out there. If I want it lent again, it means I would have to disconnect and then reconnect. Once I do that, it should learn the address all over again. Right, so if you use the same command, I'm sure this time around, it might have. Okay, still hasn't learned it yet. Because no communication has gone on. I should do a ping or something before it should see it. But I just have one single device, so I might not be able to demo that. But you can always try it. This can be done in Packet Tracer. You should equally get similar feedback. Right, are we good? Okay, so fine. That's the end of the class, but let me just chip in this and we go away. So we have what we call a broadcast. We mentioned it as we went along the class. So a broadcast means basically a group of network devices that will simultaneously receive a layer 2 broadcast frame. Right. So where I have a single switch that defines my broadcast domain, because if a broadcast frame is sent, every single device attached to that particular switch is going to receive it. Right. Okay. So I know this has been a very lengthy class. It's been very bulky, so many things here and there, but then it's not really much of a big deal. I think by the close of today, all the videos should be online, so you get to see them. And if it's a review you want, you can always do the review again, and then we go on with that. Your lab is equally going to follow. Yesterday, I worked on the, how do you call it? I've worked on your other one, the old ones. I'm trying to structure them properly. So I'm sure if you have gone to the Google class, you should see it in there. And now this is the structure of the lab in your Google class. I think there's a quiz which you have to answer. With the first model, I made a mistake of adding the lab to the quiz. And the labs require you to do it in Packet Tracer. When you do it inside Packet Tracer, I expect you to submit it. So let me show you how that is done. Let me open Packet Tracer. Because you have to save the work. When you do your Packet Tracer work, please try and save it. So let me open Packet Tracer. So I can close this, so I don't have too many things running. Let me close this as well. Then okay. Okay, let me quickly log into Packet Tracer and show you. Yahoo.co.uk. Okay, so that's our Packet Tracer. So let's assume if you do any work in Packet Tracer, let's say, let me just pick some routers and pick a couple of, let me pick some switches. So I have 2 switches here, like this. Right, and I pick my cables and I connect them. So I'm just doing a lot to connect here. Fine, let me just leave it like this. I'm not even connect this at all. Yes, so let's say this is a topology you've drawn and you want to save this topology and send it as a work. So all I do is I come here like this, I click on file, like when you do your normal save, you save, and if you go to a location, you know where the path is. So you have to choose where you want it to go. But I'm going to create a folder here and name it Packet Tracer. So I open that Packet Tracer folder of mine. Then you can name it with a module number. So let's say if it's module 1, it's just module 1 lab or something, probably with your name or something. So module 1 lab, and I just type Jesse, like that. It saves it like this. So I just save. I've saved this file. So I can, maybe I'm done with my work, I can close Packet Tracer. You want to save your work, yes, so you save and you close. Now, I would open my browser. I don't know how you guys have your Google Class running. I'm sure most of you have it on your phone just to do the work. But then for Packet Tracer, you might have to sign on. You're not going to be using Packet Tracer from your phone. You're likely going to be doing it from a PC. So let me do Google. So I show you. So let me drag my browser here. So I have my Google account logged in. And I go to Classroom because I'm one of you. I set myself up here. So I click on Classroom down here. When you go to the Google Apps, click on Classroom. All right, so there's a class all of you are on this class currently. So I click on this class and I gave an assignment. So yeah, so let's say I'm just using this as a demo. So let's say there's a Packet Tracer Lab demo. Let me open it. So I'm here, then I would go to this place like this. This was the lab, this was the assignment I gave you. So you see it there like this. Right. You'll see your topology drawn. So if you're done with your Packet Tracer work, all you do is you would add file. So you click on the add file and you browse to where the Packet Tracer was saved. In this case, I have a folder in documents and Packet Tracer is here. So that's it. Model 1 lab, just this one. So you just select it and then you upload it. Right. So once you upload it, you are done. You just upload. That's all. Like this. That's the example you see there. And then you just choose submit. That's all. Right. So you submit it and then I should mark it and send you a response or something. You see it. Right. I hope it's good. And I believe we cannot follow through and do it. Fred, I realized I sent you the invite. You haven't joined yet. So check your mail. There's an invite from Google Classroom. Just try and join it up. But I think everybody else is there. I think Ransford, you have been able to join it, right? Then Eric, I think you're also there. Is that not so? Yeah. Okay. Sure. So we're good. I expect you to turn it in from that side, and then we should be good to go. So I believe this class has been quite successful. Thank you for your patience and your time. I look forward to seeing you guys tomorrow. I don't think I have anywhere going early morning tomorrow, so we'll have a class and we can call it a week. Okay. Thank you and have a nice day. So this has been recorded. I'm banding up today, so you'll get all your videos. I know it's been